Thermodynamics in Biosystem, Module 4, Properties of Pure Substance, Segment 5, Ideal Gas Equation of State. With me, Yusuf from School of Life Sciences and Technology, Institut Teknologi Bandung. Previously, we have discussed about phases of a pure substance, phase change processes, property diagrams, and property tables. In this segment, we will discuss about ideal gas equation of state. Property tables provide very accurate information about the properties, but they are bulky and vulnerable to typographical errors. A more practical and desirable approach would be to have some simple relations among the properties that are sufficiently general and accurate. Any equation that relates the pressure, temperature, and the specific volume of a substance is called an equation of state. Property relations that involve other properties of a substance at equilibrium states are also referred to as equations of state. There are several equations of state, some simple and others very complex. The simplest and best known equation of state for substance in the gas phase is the ideal gas equation of state. This equation predicts the PVT behavior of a gas quite accurately within some properly selected region. Gas and vapor are often used as synonymous words. The vapor phase of a substance is customarily called a gas when it is above the critical temperature. Vapor usually implies a gas that is not far from a state of condensation. At low pressures, the volume of a gas is proportional to its temperature and can be expressed by equation 4.6, which is called the ideal gas equation of state, or simply the ideal gas relation, and the gas that obeys this relation is called an ideal gas. The properties of an ideal gas at two different states are related to each other by equation 4.7. Is water vapor an ideal gas? This question cannot be answered with a simple yes or no. The error involved in treating water vapor as an ideal gas is calculated and plotted as shown in the figure. It is clear from this figure that at pressures below 10 kPa, water vapor can be treated as an ideal gas, regardless of its temperature, with negligible error less than 0.1%. At higher pressures, however, the ideal gas assumption yields unacceptable errors, particularly in the vicinity of the critical point over 100% and the saturated vapor line. Compressibility factor. The ideal gas equation is very simple and thus very convenient to use. However, as illustrated in the previous figure, gases deviate from ideal gas behavior significantly as states near the saturation region and the critical point. This deviation from ideal gas behavior at a given temperature and pressure can accurately be accounted by the introduction of a correction factor called the compressibility factor, which can be defined by equation 4.8. Obviously, Z equals to 1 for ideal gas, whereas for real gas, Z can be greater than or less than unity. The farther away Z is from the unity, the more the gas deviates from the ideal gas behavior. The compressibility factor for various gases are shown in the right figure. From the compressibility chart, we can observe that at very low pressures, gases behave as ideal gas regardless of temperature. At high temperatures, ideal gas behavior can be assumed with good accuracy regardless of pressure. The deviation of a gas from ideal gas behavior is greatest in the vicinity of the critical point. In the next segment, we will discuss about other equations of state. Until then, I am Yusuf from Institut Teknologi Bandung.